Welcome friends, welcome to our YouTube channel Crystal Learning. Today we will see the concept of effect of cutting force on depth of cut and feed rate etc., which comes under the subject of manufacturing processes and in manufacturing processes in machining. Let's see the question. The question says, when turning mild steel, if area of cross section of cut remain constant, the cutting force will be minimum if depth of cut is half the feet per revolution, approximately equal to feet per revolution, 1.5 times the feet per revolution, 2 times feet per revolution. This question came in SSC-JE in 2012. Let's see the explanation. So we know that cutting force is directly related to power consumed. As the cutting force will increase, power consumed will also increase. So we are defining a term that is specific cutting energy Ks as the power Pc to cut a unit volume of material per unit time, and that quantity is defined by Z. So for turning operation, Ks, that is specific cutting energy, is defined Pc upon Z. Pc is given by cutting force into cutting speed, and that Z parameter is given by depth of cut into feed rate into velocity, cutting speed. Cutting speed will cancel out, and Fc upon Tf. Its units in Newton per mm square. So we see that its different name is also specific cutting resistance. This parameter depends on type of work material, meaning that for mild steel it will be different, for aluminum it will be different, but it is not a material constant. Why? Because it depends on the cutting condition. So that cutting condition is undeformed chip thickness H, which is depending on feed rate F. So if you are able to make these two values constant, then it will become a material constant, which means that for mild steel it won't change if you are not changing these two parameters. So Kinzel and Victor, these two scientists, gave an empirical relation to calculate the value of Ks, that is C, a constant, H minus Z. Z and C constant given for that material, and H is undeformed chip thickness. So this figure is for oblique cutting, and this is for orthogonal cutting. Area of cut is given by F into T, and here B into H. Okay, B into H, and H is undeformed chip thickness that comes by multiplying feed rate into sine of X, that is cutting agent. So from equation 1 we can write Fc equal to Ks into T into F, and suppose that for mild steel in the question or anywhere it is saying that Ks take value as this constant value. That means for that condition you are not changing the feed rate F and angle of approach. They are constant. So this becomes constant. So you can leave out and we can use the proportionality sign, that is Fc is depending into T cross F. And now area is also given B into H, and area is T into F for orthogonal cutting. So it seems that if area of constant remains same, then Fc, that is cutting force, will not change. But in actually this logic is wrong. Okay. So we will see why it is wrong. So this is the figure. Experiment was done on mild steel during turning. Cutting speed was kept 10.668 meter per minute, and one condition is given is area of cross section of cut remains constant. You are not changing area of cut. Then a minimum cutting force occurs when depth of cut approximately equal to feet per revolution. That is, minimum force is observed where this ratio value is 1. That is, feet per revolution divided by depth of cut is 1. Then minimum cutting force is there. Now let's see through a numerical value which will make it more. This region is given as 1 from here to here. This exact point is given as 2, and greater than this value is region 3. So ratio R1 is F upon T, feed rate upon depth of cut, that has to be less than 1. R2 is equal to F by T equal to 1. R3 equal to F by T greater than 1. Suppose we are taking, this is just for understanding purpose. Okay, so feed rate is 4 and depth of cut is 4. So value is coming. That means area of cut is 16. In this case, now we have to keep this area as constant, area of cut. So now our value will change like this. Feed rate has to be less than 2, less than depth of cut, that will be 2 and 8, and the multiplication 2 into 8 equal to 16. So we got 16 area of cut and we got a ratio less than 1. And now again, now feed rate has to be greater than depth of cut. Okay, so 8 by 2. Here also area is 16. So we see that in three conditions we are keeping that area of cut same, but we are getting different cutting forces. This shows this this shows that cutting force will depend upon the ratio of feed rate and depth of cut, and this feed rate and depth of cut ratio will also depicted by the shape of the cut. Okay, what is the shape of the cut? Because if F and T is changing, definitely the shape of the cut will be changing. So we see here that the minimum cutting force is achieved where depth of cut is equal to feed per revolution. From these examples we have seen. So now coming back to the options. So this is the important graph from where you can get the understanding to solve this problem. So for this problem, right answer is approximately equal to feed per revolution. I hope you enjoyed this lecture and this tutorial. Some of the funda or concept has increased. So this way, by solving questions, our knowledge is getting better day by day. So meet you next time. Have a nice day.